again, I'm the awesome tutor, and today we're going to be looking at total internal reflection and a bit more on refractive index, but this time using the critical angle. So first of all, let's recap refraction a little bit. Remember, refraction is when light changes direction when it changes speed. Now look here, the ray of incidence, and then the light refracts and bends towards normal, right? And from the other refractive index video, we know that as the angle of incidence increases, the angle of refraction also increases. So if the angle of incidence here was bigger, then the angle of refraction would also be bigger. Now, what if we look at the light refracting away from the normal, from glass to air instead? So remember now that this is the angle of incidence, and the ray refract, but this time away from the normal. And in this case, this is also true. As I gets bigger, R gets bigger. But what if the angle of incidence is big enough? That the refracted ray bends so much away from the normal that it actually skims across the surface of the glass. If this happens, then the refractive angle is going to be 90 degrees. And the value for the angle of incidence is now called the critical angle, which can be described as the angle of incidence that provides the maximum refraction of light. So yes, let's just recap, because I know it's a lot to take in. So as the angle of incidence gets bigger, the angle of refraction gets bigger. Let's look at it going from the glass to the air. Angle of incidence gets bigger, then the angle of refraction will get bigger. But what if the angle of incidence becomes so big that the refracted ray refracts so much that it skims across the surface of the glass? In this case, the angle of incidence is the critical angle. And the critical angle of glass is around 42 degrees. And let's actually zoom into this example. Okay, so again, in this case, the angle of incidence is now the critical angle. And there's actually another way to calculate the refractive index of the glass. Before, you could use the sine of the angle of incidence over the sine of the angle of refraction, but from air to glass. In this example, it's from glass to air. And if you get given the critical angle, you can work out the refractive index without anything else. So the refractive index is going to be 1 divided by the sine of the critical angle. So say the critical angle of the glass was 42 degrees. The refractive index of the glass will be 1 divided by the sine of 42 degrees. Let's find out what that is. The sine of 42 degrees is 0.669, blah, 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 blah. And calculate the refractive index, 1 over whatever the sine of 42 was. So 0.669. 1 divided by that gives you 1.49 to 2 decimal places. And they might give you a question on this in the exam. So now let's move on to the actual topic of this thing, which is total internal reflection, and you'll see how this links. Okay, so as we said, if the angle of incidence is equal to the critical angle of the glass, then the refracted ray skims across the surface of the glass. But what if the angle of incidence is bigger than the critical angle? If the angle of incidence is bigger than the critical angle, you would naturally expect that this would bend more. And so, instead of the ray being refracted, the ray is actually this is a bad pen. The ray is actually reflected. Because if the angle of incidence is bigger than the critical angle, it cannot refract. If it goes back this way, then it is reflection. And this is called total internal reflection, because the reflection is happening within the actual object. Not like this, this is a mirror, and then that's angle of incidence and reflects. No, this is happening from within the object. So this is total internal reflection. And remember, in reflection, the angle of incidence always equals the angle of reflection. So this is going to equal this if it reflects. Therefore, imagine one long block of glass. And we do the same thing here. The angle of incidence is bigger than the critical angle of the glass, so that the ray reflects. And in reflection, the angle of incidence is always equal to the angle of reflection. So then it's going to be reflected. Then what? This is bigger than the critical angle, and because I is equal to R, this will also be bigger than the critical angle. So then this will also be reflected again, and again, and again, and again. And that is total internal reflection. And it has many uses, two of which, okay, maybe three, we'll go over next. Okay, so let's look at the endoscope. The endoscope is a medical device that is used to see inside the body, and it is inserted via the throat. It contains two bundles of optic fibers, which I shall explain what they are next. And one of the optic fibers, one of the bundles, it shines the light. The other is used to see the internal surface. So imagine this one long, this is the endoscope. And then one of the optic fibers, it shines the light. So where's the light source? It's coming from inside. And then because it's shining the light at the internal surface, say the stomach, so then e.g. the stomach, the light will be reflected. But it will be reflected so that when it enters the glass it refracts, okay? But you don't need to know anything about that. Just what happens inside the actual endoscope itself. So, the light enters, and then we have total internal reflection. It uses this to get the light all the way from the internal surface to either someone's eye, like a doctor, to see the internal surface, like the stomach of the patient, or a digital camera is used, and the light is shown into that, so an image is displayed. And let's look at optic fibers. So optic fibers are like these long strands, and they use the same principle: total internal reflection. And optic fibers are basically used for like broadband signals and stuff like that. Okay, so laser light. Lasers are just an intense beam of light. You do not need to know how you get from light to lasers, but just that it is an intense beam of light. Laser cutting, that's pretty self-explanatory. Use lasers to cut objects, usually metal. And the good thing about laser cutting is the energy can be focused on a very small surface. So then you can use it in surgery. Like with the endoscope as well, like to, say, cut away a damaged tissue. And on a very small surface, so it's more accurate. Now also the color of the laser can be matched to the type of the tissue. And you can choose a suitable laser source for more effective absorption of the actual laser. And now for eye surgery, so you are applying the laser light into through the pupil of your eye, so on the retina. And it corrects the visual defects of your eye, so are you long-sighted or short-sighted, it will correct those defects. But the light is only applied for a very short time, because obviously lasers in your eye, that's going to damage them. If the laser is on your eye for too long, it's going to damage them. So there has to be safety precautions when using lasers in general. So like special safety goggles that reduce the brightness of the laser or perhaps reflect it off. And that's basically, you just need to know a basic understanding of the uses. You don't need to know the uses in too much detail, but they might give you these examples in your exam, like a case study. And now onto the exam question. Okay, so this is the exam question which actually showed up in one of the exams. I think it was the 2014 exam of the higher tier. So this is a laser source, and then as you can see, the light is totally internally reflected, total internal reflection. And this is an optical fiber. Now, why does the light ray stay within the optical fiber? Well, from watching this video, you should know that this is due to total internal reflection. And why is the light totally internally reflected? Because the angle of incidence is greater than the critical angle. And so the light is reflected, not refracted. Reflected, not refracted. And that leads to total internal reflection. Now the mark scheme says the answer is because the angle of incidence is greater than the critical angle, and that gives you the 1 mark. But it also says except the light is totally internally reflected. So basically what we said here. Now, it says that the refractive index of the material used to make the optic fiber is 1.5. And it wants us to calculate the critical angle of this material. It's 2 marks. Well, it also says use the correct equation from the physics equation sheet. So, as I said, you will be given an equation sheet with all the useful equations that you're going to need in the exam. And the equation to find out the refractive index using critical angle is 1 over sine of the critical angle. Well, you don't want the refractive index, you want the critical angle. So, rearrange it. So then the sine of the critical angle is going to be 1 over the refractive index, which is 1.5. So use your calculator. What is 1 over 1.5? That's 2/3. But you don't want the sine of the critical angle, you want the critical angle. So use the inverse sine function on your calculator. So inverse sine of 2/3 gives you 41.810 blah 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 blah. Just leave it as 41.8. And the mark scheme says that the answer is 41.8. There you go. Bye.